So till now we have been studying refraction due to plane surfaces. Now let's jump on to refraction due to curved surfaces. And even in curved surfaces, we would be focusing on spherical surface. That is easier to understand. That's the only reason. Mathematically convenient. So let's say this is an interface, spherical interface between two media. This is media 1 having refractive index is mu1, and this is media 2 having refractive index mu2. Let's assume for the sake of it that mu2 is greater than mu1, which means that this medium over here is denser, optically denser than this medium. I have to study image formation essentially. This point over here, you can write P, and over here you have the object placed. This spherical surface must be part of a big sphere, and that big sphere must be having a center of curvature. That would be on this side only. Let that be here. This point image, or rather object, would give out a lot of rays. This ray would fall normally, or this is normal incidence. So essentially what will happen is this would pass unrefracted like this. But a ray which goes off this line over here, let's draw a normal for this ray. This is my normal. This angle over here is the angle of incidence, I. I know that this is a denser medium, which means my angle of refraction must be less than angle of incidence. So it would bend towards the normal, which means had it been the same media or medium all throughout, it would have been this path, but it has to bend towards the normal. So it would go something like this. Now this ray over here and this ray over here, they meet at this point, and image formation is always due to intersection of two rays after reflection or refraction. So this is your I. Now let's suppose this angle is alpha. Let's say this is your beta and this is your gamma. And what exactly is this angle? Angle the refracted ray makes with the normal is angle of refraction or refraction angle, R. Now in this situation I know that this is a very small length, so I can assume that the circular arc thing is a straight line in all practical sense. Let's label this point as X, and let's draw a few triangles. What you find out is in this triangle, triangle OXC, I is equal to alpha plus gamma. Similarly, in this triangle XCI, gamma is equal to R plus beta. Now this gives you R is equal to gamma minus beta. So now here you have I and R. I know how to relate I and R. Sin I upon sin R gives you the ratio of refractive indices. Over here, sin I upon sin R is going to give you mu2 upon mu1. What exactly is sin I? Sin I is sine of alpha plus gamma. This is sine of alpha plus gamma. And similarly, sine of r is sine of gamma minus alpha. Rather beta, not alpha, beta. I'm sorry. Equal to mu2 upon mu1. In all the situations of geometrical optics, we have to assume that the rays are paraxial, which means alpha is small. In effect, beta, gamma, IR are also small values, which means alpha plus gamma is small. So I can approximate sine of alpha plus gamma as just alpha plus gamma. So I can just simply write this thing as alpha plus gamma upon gamma minus beta is equal to mu2 upon mu1. Cross multiply them. What you would get is alpha mu1 plus gamma mu1 equal to mu2 gamma minus beta mu2. Over here now, take this gamma thing to one side and this mu2 mu1 in the other side. What you would get is alpha mu1 plus beta mu2 is equal to mu2 minus mu1 times gamma. Why? Shift it over here. There's a negative sign which is coming with this guy, and there's a gamma thing which is common with both the things. Take that gamma outside. Now over here, alpha, beta, gamma are angles, and inherently they are of very small magnitude. So I can replace alpha, beta, gamma with tan alpha, tan beta and tan gamma. So let's replace them. What exactly is tan alpha? Tan alpha can be found out with this triangle OXP, PX upon PO. So this becomes PX upon PO into mu1. Beta can be found out from this triangle PXI. Tan of beta is equal to Px upon Pi. I'm approximating beta as tan beta. Px upon Pi times beta, rather mu2. This equals mu2 minus mu1 times gamma. Gamma can be found out from this triangle. Tan gamma is xp upon pc. Or rather px upon pc. Xp, px is essentially the same thing. That's the length of distance between p and x. In this equation, if you're observant enough, this px thing would be getting cancelled away. Because px is not 0, I can cancel them away easily. So if you remove the px thing away from this equation, what you would be left out with is mu1 upon po plus mu2 upon pi. This is mu2 if you have any confusion over here. And mu2 minus mu1 upon pc. Now half the mystery has been solved, but still a part of it is left. I have to invoke my sign convention thing. Sign convention says that in the direction of light travel, all the measurements are positive, which means to the right of pole, all would be positive. PC over here has to be positive. Rather, PC is always positive. I mean, radius of curvature has to be positive. So if I replace PC with radius of curvature, I won't have much of a difference. It would be simply R, value of radius of curvature. But if I want to replace PO, O is on the left side, which means if I want to replace it with object distance, my object distance essentially is of a negative nature. So I have to adjust that negative sign over here because PO is positive, PI is positive, and PC is also positive because these are essentially lengths or magnitudes. So they cannot be negative. But if U is negative, I'll have to account for that. So let's do that. Which means what we left out is mu1 upon minus U plus mu2 upon this thing over here, V, object distance, as it is positive, simply V, and as radius of curvature here is positive, so simply R. I can rearrange this thing, and what I would get is mu2 upon V minus, this minus thing goes over here, is equal to mu2 minus mu1 upon R. This is the equation for the image formation due to refraction at spherical surface. Now, we have taken a surface which is of convex type, but this is equally valid for convex or concave. Ideally, I should redraw this diagram for concave and do similar calculation for concave too. But it doesn't make sense because I'll draw a similar diagram, I'll make the similar approximations, and I'll ultimately land up with the same thing. Why? Because I have taken proper sign convention, which means this is valid for all situations. And again, the ground assumption is that these rays are of a paraxial nature. It's the only assumption which I have made over here. Now, this essentially forms the basis for formation of lens, because lens essentially is a medium inside a bigger medium. And how exactly is that possible? Let's understand that idea. In a lens, what happens is you have two spherical surfaces and both of them have different radii, and inside you have a refractive index of the material of the lens and outside you have vacuum or air, whatever you want to say. So here you would have a refraction, and here also you would have a refraction, 1 to mu and mu to 1. We'll come to this gradually, but let's complete this thing at this stage. Now, this was for a point object. Most of my objects are not point objects, they are extended objects. So what will happen to an extended object? So if you take a very simplistic situation, this again is a concave surface which I am dealing with. This is your center of curvature, this is your P, this is your object over here. If you pass a ray along the C, which means ray of light is falling normally, so it would go unrefracted because this is normal incidence. For normal incidence, my angle of incidence is 0, so angle of refraction will also be 0. From this, even this is a case of normal incidence, it would also go unrefracted. So I will just draw image like this. Now, this angle is equal to this angle, vertically opposite angles. This is 90, this is 90, which means these two triangles are similar. If I take this as O and this as I, what I would get is, if this is your AB and this is your A prime, B prime, so A prime, B prime upon AB is equal to, in this situation, their orientation is reversed. It is vertically inverted, which means I'll have to account for that. So over here, this height over here is of a negative value. So I'll just write a minus h of the image by h of the object. This is your magnification, and this is nothing but this length OC upon C, rather, yeah, this is OC and this is CI. What is OC? OC is PO plus PC, and your CI value is PI minus PC. PO, PI, PC are all magnitudes, so they would be inherently positive, right? If they are inherently positive, I'll have to substitute U, V and R by accounting that positive negative thing with sign convention. P over here is in this side, so it would be negative in the sense of object distance, which means I can say magnification is equal to, what exactly is PO? PO is minus of U. What is PC? Right hand side, so positive. PI, right hand side, so positive. V minus R. And I also know that U and V are related by this equation. So using this and this, what I finally get is magnification is equal to mu1 into V upon mu2 into U. See, this result over here is not that important as far as examination point of view is concerned, but still this is a good exercise so as to complete the idea of magnification. If you have an extended object, obviously it would be inverted or not inverted, it would be magnified or not magnified. So that information is hidden in this formula. M is equal to mu1V upon mu2U. So in the next video, we'll try to find out how lens is made and how do we understand the formation of image by a lens.